Welcome to the special edition of the Uptime Wind Energy Podcast, and we are in Roskilde, Denmark, at the 5th International Symposium on Leading Edge Erosion and Wind Turbine Blades. And I'm here with Nicholas Gaudern of PowerCurve and Rodolfo Meleiro of Arthwind. So we have sort of a world perspective here on leading edge erosion. we have Europe, Brazil, which is a lot of wind energy there. Thank you, Rodolfo, for being here. And I'll try to cover America as best I can. So this has been a really interesting conference. It's held at DTU, this is the Wind Energy Center. So this conference has been organized and it has international flavor to it. We saw presentations from India, Denmark, obviously. There were some German presentations, Japan, China.
U.S.
Sandia has been here. So there's there's a paper from Cornell today. So there's been all sorts of people worried about leading edge erosion, and I think it's a really hot topic. And that's the reason why I came to see the action here, because there's so much that we don't know. And I figured, well, if anybody does know, it's at DTU, so it's time to get over there and to find out what's going on. So this whole podcast is really to discuss what we have seen and heard, and try to figure out what the state of the industry is and where it needs to go. And just first impressions, really. One of my first impressions, I'll just start. One of my first impressions was we have a long way to go.
Yes.
That we don't know a lot.
Yeah.
And I have been shocked so far. So we're sort of at the end of day 2. And day 1 was pretty intensive on the sort of the mathematical, computational side.
Yeah.
We don't know a lot.
We've had a lot more materials as well today. So I think it's nice that we have that really cross-disciplinary approach here. So we've got materials, we've got structures, we've got data, we've got metrology, meteorology, aerodynamics. So it is bringing all of these expert field together, which I think is really important. But there's also the risk that there's a lot of noise.
Right.
Because obviously there's kind of issues to be resolved in all of these different fields. And then, it may make it a little bit harder to focus on what really matters, I think.
Right. There's a lot of data smoothing that's happening at the minute, from what I can tell, and different approaches to data smoothing. And I'm not even sure everybody has settled on that.
No, and I think we had a discussion at the end of the day yesterday, like a shouting across the lecture theatre kind of discussion at the end of the sessions. And I think what was clear is there is more of a consensus about the AEP losses that we're seeing,
right?
Which is important, and that's really helpful, because I think if you start seeing big scary numbers like 15, 20, 25% AEP losses, sure, those might exist in a very extreme scenario on a very particular type of turbine, but I really want to make the point here that is not the norm at all. We wouldn't have an industry if turbines were losing 20% AEP every time they got some erosion.
Yeah.
So I think that's been a really nice thing for me to see this show, that there's conference. There's been a lot more, convergence on small but significant numbers. 1.5%, 2% AEP losses. That's plenty to worry about. We don't need to.
No, I think that's right. Is because Rodolfo and I were just talking about that before we recording here. We saw a presentation that said 25%, right, this morning, and everybody in the audience is like, no, they can't be. But it does matter where you are in the world, though.
Yes, it does.
And having seen more recent pictures from Central America, India, some places in Brazil. They have really tough rain environment. What happens in the United States is not what happens in Brazil.
Yeah, totally agree. Well, I'll give you a spoiler of the data I'm bringing. Half of Brazilian fleets right now does not have LEP anymore. They have delaminated. Yeah.
Okay.
So that's the status Brazil has right now. Brazil is a relatively new industry, so the first older wind turbines are reaching 10, 12 years.
Sure.
So, and now some of those are requiring the maintenance, and the owners are looking at, and that's what we're seeing. We're seeing very degraded leading edge.
Like put your hand through the leading edge kind of degradation?
There is that, but that's not common. That's not common.
Okay.
But lack no more linear protection, no more top coat, laminate exposed, laminate damage, that's a lot.
So it's a structural repair. They're so
It's
far
a structural
down.
repair already.
Okay. All right.
So, and we were discussing that before, that's extra cost.
Yep.
Besides reapplying the leading edge, having to do the laminate repair, that's a very extra cost, extra time for the machine stoppage, extra problem for everybody.
Yeah.
Well, I think that's why we're all so concerned about it. And this is the discussion that was held last night as part of the IEA group, right? What was the name of the IEA group that was
So
discussed?
there's the IEA Task 46, which
Task 46.
is focusing on the leading edge erosion, and then there's also, it's not IEA, but there's a Danish funded project, EUDP funded, called LEARCAT, Leading Edge Roughness Categorization. So that is involving a lot of OEMs. So we've got Vestas, Siemens, Suzlon, LM, led by DTU and Power Curves also part of that as well.
I guess LM is representing GE. We don't leave them out.
In a sense, yes.
Right? Okay.
Yeah, exactly. So LEARCAT is also feeding in and collaborating with the IEA task, because there's a lot of shared knowledge and goals there.
But they're going different directions, though. That was my opinion, being an electrical engineer and a lightning person, is that the IEA was about trying to create some categories so that in a damage report, they could say it was leading edge erosion 2. But
Yeah, I think the IEA is being more broad. You know,
Okay.
they're trying to bring in structure and repair considerations and a bit more of a, it seems a little more holistic, whereas LEARCAT is very much focused on the aerodynamics and the aeroacoustics and the impact of different types of damages. So there's no structural focus there, for example.
right, and I think this is where I think that program has a lot more to deliver in terms of what value it would bring to the industry. In that program, they're actually taking real damage off of blades, like taking a mold off of a damaged blade,
Yep.
then creating a leading edge that they're putting onto a blade in a wind tunnel, and actually doing real experiments in the wind tunnel to measure AEP loss, drag, essentially drag to lift, and then acoustic noise to come off different kinds of damage.
And that's really important because, you know, we were talking just at the start of this session about what is the AEP loss number?
Right.
Because you have to have a realistic number that people can believe in and trust. Because otherwise, it either gets way too much attention and people get scared, or it doesn't get any attention at all.
Right.
So you kind of have to find that balance. Now, I think LEARCAT should deliver a lot towards that. So there's this fantastic wind tunnel here, the Poulacourt wind tunnel, really big, impressive new facility. And I was up there yesterday having a look at the first models for the LEARCAT project that are going into the tunnel. So they've 3D printed leading edge modules from these laser scans and these molds that have been taken in the field. And then they can carry out these really precise measurements to say what is the lift and drag impact.
Because the ultimate result of this is to help wind turbines in the United States and in Brazil, which have tend to have a lot of leading edge damage, probably more than what I've typically seen in Europe. At least
On average, probably
in Europe.
Yeah.
Yeah. So the issue then is computationally, you want to be able to take drone scans. This is what AeroVista does. This is the Power Curve AeroVista approach to it, was basically taking some scans, some photographs, and then driving that to an AEP loss number so that you, the operator, can understand, when do I schedule maintenance or do I schedule maintenance?
You need to know when to make a decision.
Yeah, we know the wind business is a business that has to stand for itself.
Yes.
So all decisions comes down to downtime, to the cost, and yes, a reliable model and a reliable prediction of how much you're losing in production.
Yes.
And how much it will cost you to repair. That's just a business case model. So that drives a decision. Okay, this month is the correct month to stop the machine, do the repair, and go back to the regular production and have another maintenance predicted for X years, X months.
And I guess the bigger the turbine is, the more important that is as well.
Totally the more important it is for many reasons, because the bigger the turbine, the tip speed is increasing. So the erosion is increasing. The bigger the turbine, bigger problems. We'll discuss that a lot.
And the more money you lose.
And the more money you lose, because you're not stopping anymore a 1.5 megawatts machine. You're stopping a 4, 5, 6 megawatts machine. So it's much more power you're losing by each minute the turbine is stopped.
Yeah.
offshore multiplies that. And that was mostly the discussion here because Europe is so much offshore and America is just getting started and Brazil is going to be doing the same thing that America is doing here shortly, right? So instead of 5, 6 megawatt machines, we're talking 10, 12, 18 megawatt machines.
Yeah.
Then it really becomes important because the cost to get out to a site to do a leading edge repair is so expensive that you'd want to do preventative approaches before you even deploy the blades, in my opinion. And that's not a discussion I heard this week, which is odd.
Not so much. No.
Why? What am I missing here? It would seem to me as an OEM that I know that's going to be a problem. I know when I put an 18 megawatt machine out in the water, then I'm going to have leading edge erosion. And I probably ought to put some protection on it just to extend the lifetime.
I think, again, I can't speak for every turbine, but from what I've seen, every recent offshore deployment will have some form of LEP.
Okay.
But of course, I think the technology has moved on a lot in recent years.
Yes.
From some of the early coatings and tapes to some more advanced now shells,
Right.
soft shells, hard shells, other kinds of coatings. And that is making a difference, but I've still seen some photos of some pretty shredded blades.
Yes, I have too. But
so-
again, that comes down to, I think it's in the part of the discussion here, I want to dive into this a little bit, is it's not just the shell, it's not just the coating. The failure mechanism for leading edge erosion has to do with the assembly of all of it.
Yes.
Because, and this is my simplistic approach to it, electrical person talking electrical things. It's much like a radio wave passing through different materials. There's impedance mismatches. It's boundaries, right? So when the rain particle hits this surface, it then puts a force or it transmits energy through this material.
Yes.
And at every boundary, if there's a discontinuity, there's a lot of force to rip it apart, to break it apart.
We saw some interesting presentation yesterday when we looking at the hail impact on leading edges as well, and that kind of impact damage you get. So offshore, it's just a much more hostile environment.
Sure.
Right? In terms of the salt, you've got that corrosion.
The UV,
effects,
I think,
the
could be
the winds. So it's tough, but it also makes it even more important to understand what the loss is.
What the losses are, I think the key, right, if you're dealing with an 18 megawatt machine, a 20 megawatt machine, the losses get to be astoundingly big.
Yeah.
And because of the cost.
Even if you're losing a
extrapolating
few
out.
tenths of a percent AEP, that's worth doing something about.
Yeah, well, I totally agree. So I think there's sort of like a multidisciplinary approach to this. One is to understand what the materials are doing, and I haven't heard a lot of discussion about that. Maybe just because the researchers are super smart and they already know when they walk in here. I haven't heard the story. I'm not catching it, but it seems like the material has a lot to do with it. The application has a lot to do with it. The laminate in which it's being applied on, the thicknesses of which it's being applied, the temperatures, the humidities, all those things play into whether that coating or that shell or whatever it is has a long lifetime.
Yeah.
And are we controlling those variables? And is the word that the researchers are writing down and is in sort of technical terms, is that being translated to the engineers and the mechanical people on the floor who are actually doing the work?
Well, I don't always like to give not example, but a fact. Every blade, 2/3 of the blade weight is manually put in by somebody into it.
Yeah.
That's the count.
Right,
You
that's
have
true.
roughly 1/3 of the blade weight in resin that goes by infusion process. It's more automated, but all the other 2/3, the paint, the fabrics, the core, everything someone puts on his back, sits in the molding position, fits correctly.
Yes.
So we're talking about a 30-ton blade, 20 tons are manually put into that blade.
So
That's
that's
true,
the
yeah.
product.
Yeah.
And then we discuss how much of the variable on the microns of thickness of coat
Right.
will affect the life. So it's some very complicated things that right now we do with control, but not that level of control.
Yeah.
Right.
So we have a lot of variables.
There's a lot of variables in the application of coatings.
Yeah, and the environments that these turbines sit in. I think that's also an important
Varies.
thing here with it. Things like rainfall, average annual rainfall, that will have a
This is
role.
Brazil, yeah.
But also that doesn't tell you the whole story. Like even among the turbines on one site, the variability in erosion can be quite dramatic, and
yeah.
it's because of this handcrafted product, this, that we've just been saying, Rodolfo, and the really local microclimates and the individual operation of that turbine. So it's really important that you get out there and you look at the turbines.
Well, and the data you provided yesterday was amazing because you looked at, 1,500 turbines?
Yes, yeah. We were really fortunate to be able to present that. So we did a project last year with one of the big US operators, one of the top 4 US operators, and we looked at a sample of their fleet with over 1,500 wind turbines. There was 8 different turbine models. So we have a nice spread of models from different OEMs.
Okay.
Rotor diameters between about 80 and 120 meters, and ages from 2 to 15 years. So we have a really nice
spread,
population. And what we found was that, firstly, there's a lot of damage. So we receive all of the metadata from the drone inspections to say what damage is and where was it found.
Right.
On those turbines, there was more than 95,000 tagged damages.
Whoa. Okay.
Yeah, so quite
pretty
a lot.
much every turbine had some level of it.
Exactly.
Danny Ellis had told me that a long time ago. He said every turbine has leading edge erosion, every one of them.
Yeah. So that's really important, because then you can start looking where is that damage, and kind of unsurprisingly, most of it is towards the tip.
Sure.
So most of it's in the outer 20% of the span, because that's where your tip speed's highest, and you're going to get that erosion starting.
But there was not, when I got to the summary, then I want to get to this point, it wasn't like a particular OEM had a particular problem.
No.
Everybody had basically the same problem. And even turbines that were next to one another at the same wind farm had a different result.
That was super interesting. So what we're finding is, by actually looking at the real inspection data and then coupling it to a model of that turbine. So, I mean, we won't go into detail, but basically we built a very nice aero model from a laser scan, a lot of CFD modeling. So we know exactly how the aerodynamics performs. You could have 2 turbines next to each other. One loses 2%, the other loses 0.5%.
Wow.
And you need to understand that, because you need to be able to prioritize what turbine you go to fix first and what to do with it.
Right. Otherwise, you're just wasting money.
Exactly. On average, over that fleet, that 1,500 sample, the average AEP loss we found was around 0.5%. So not dramatic, but enough. But the spread was some turbines losing nothing, some losing over 2.5%.
Okay.
So the spread is large, and some of it's quite dramatic.
So there is an inconsistency, I think. Like if I were making a product, I would like to see them all the road roughly the same. And that's not what's happening today.
No.
And is that coupled to some of the more materials-based discussions we've heard about today, which are focused around the mechanism in which leading edge erosion happens, that we're just not paying that much attention to it? What is driving that? Or is it because when I get out in the field and, different lifts and different handling techniques, and this blade set out in the field before we put it up?
I mean, I'm interested particularly to hear your thoughts on this, Rodolfo. So I know you've spent a lot of time in factories over the years, but I mean, cost. I want to say cost. There's such a huge drive for cost out in the industry. That's going to affect your solutions, your leading edge protection solutions, finish quality.
For sure. I have heard that more than once regarding which solution the OEMs decide to put on the blades, and cost is a driver for that too.
Sure.
But I think the biggest cause for all this variation is the nature of the business itself. As I said, we have too many manual labor operation. I don't know if you guys know, but right now I'd dare to say that most, if not all, of the blade leading edge is applied by roller.
Yeah, that's my impression.
And I have also, I think it's almost an artist's work to apply 15, 20 meters of leading edge and assure it to have 0.1, 0.2 millimeters thickness without variation.
Yeah.
So there are variation, there are measurements for sure, but you don't measure, you don't do the wet measurements every 200 millimeters.
Right.
So you have variation in this region, and that variation is blade by blade.
Yeah, and I think
each blade is a part artisanal work.
Yes, yeah,
But partially it is.
Yeah,
it is.
And I think you do. Cost is obviously really important, because the reason that we're able to have such an international symposium today is because the industry has been really successful in recent years at driving down cost, increasing
Yes.
deployment. I mean, wind energy is so big now. And even for someone who's been in the industry for a few years, that was kind of hard to imagine 10, 15 years ago.
True.
So cost is important. But I think now we're getting these huge turbines producing so much energy, you can't afford any kind of downtime. You know, I've heard stories of blades on offshore wind farms being brought back to shore for leading edge repairs because the erosion is
Wow.
so bad. I mean, imagine the cost of doing that.
That's insane.
And I think you're not going to want to go for your super robust, super high cost LEP solution on all turbines.
No.
But for ones that are going to be in these extreme offshore environments, you probably do.
I haven't even heard discussions about what the OEMs are offering, if anything. And I know there's some big operators here. And I thought they would be asking very direct questions. We use X. What if we change to Y? Question.
There's a lot of products out there at the moment, and there seems to be a new LEP product quite often, I would say, at the moment. And there's, again, that's why real trustworthy numbers come into it in terms of losses, because
They're all over the place. The
LEP
numbers.
changes aerodynamics, right?
Right.
But I do think that maybe sometimes operators and OEMs get a little bit too hung up on a few tenths of a percent.
Right.
So they say, okay, well, compared to my polished wind tunnel model, if I put this LEP on, the aerodynamics is a bit worse. And I can measure it. And sure you can, and you should care about the small things. But if it stops the erosion happening, that's the bigger
You're
thing to
better
worry
off in
about,
the long
maybe.
run.
I think the business case up to now, the driver for the cost reduction in the industry was wrong. The OEMs always think about the machine price.
True.
And it must be seen the lifelong operation of the machine price.
Yes.
That's cost is important. And it was less important on the old turbines because they were more robust.
Yeah.
They have less problems for many reasons, even though they have a lot of problems.
Yeah.
But we are reaching something that's strange because everything improved. The quality improved of the production, the quality of materials, our knowledge improved, but you're having more problems. And I think that this case of the leading edge is a possible improvement to, for sure, investing in apply a stronger leading edge in the factory is 100 times less expensive than applying in the field.
Yeah. And that's I think that message is getting heard more and more, is it's better to get it out of the factory correct than have to do it secondarily. But, you know, the United States, what do we have, 77,000 wind turbines running currently, something like that. There's a couple 100,000 blades.
Yeah, there's a lot to
probably
do.
need, right. There's at some point, right, you can do only so much in the factory. The vast majority of the problem in Brazil, United States, even Europe, is you're going to have to deal with what's out there right now because you need to extend the lifetime. I know the weird thing for me sitting in there is they're talking about 25-year lifespans on turbines here, and I'm thinking 10 years and it's over. In the United States, they're going to repower this thing and it doesn't matter. And the model is totally different.
That is very different. I mean, I think if you look at lots of European countries, particularly Germany, they do run the turbines a long time.
They do.
And there's a lot of focus on life extension and really squeezing everything out. But I agree, all the customers we work with in the US, it's this perpetual conversation about when are we going to repower, when are we going to repower.
Right.
And they do consider a much shorter time horizon, I think.
And that shorter time span in the U.S., my thought is, and it's sort of on the same wavelength as Rodolfo, is put a better LEP on out of the factory if you can. If you can't, most likely they're not going to buy that, right? The operators typically don't do that. All right, so you got 2 years of warranty. You got 2 years of warranty, and then you own it. And the leading edge protection may not be included in the warranty. Depends.
If it's normal wear out, it's not in
It's not in there. All right. So the model then, in my mind, is if I have a 10-year lifespan, and I'm thinking U.S. right now, at year 3 or 4, I'm going to have leading edge erosion. Now, it won't be bad enough that I have to go and do a bunch of structural repairs.
No.
But what I will do was I would get a robot out there or something and get that leading edge paired and at the same time put VGs on.
Check if the business case is there, right? Again,
Well,
it comes
I think it
down
is.
to the simulation.
I think the business case has to be proven by simulation, right? That you
Yes.
have to go look at the model. The model in my head is based upon what, Nicholas, you have told me.
Yeah.
So I'm running the calculation up
Yeah.
here. But yes, I think if you use something like an AeroVista to do the calculation, I think what you'll find is you put it on at year 3 or 4. You're trying to get to year 10, right? So you're trying to make this blade not touch it for about 6 years, maybe 7.
Yes.
The way to do that is to put on a better LEP product, put on VG, so at that last year 9 and 10, it makes you power.
Yeah.
Just missing one link, which is also a driver for the industry, inspection.
Inspection.
So
Yes.
that's what's missing
That's
in
true.
this case.
That's true,
Because I think that's the point. I think I have always, when I come to this conference, I have 2 questions I try to see if we're moving to answer. First one is how much we lost with the erosions, how we can prove that, and then put a stone on top of that, because we totally agree. We're all on the same boat, that we have lost. But yes, when we still see numbers from half to 25, we don't have a big alignment. And the second question is, how much time did my LEP last?
Yes.
So those are the 2 questions. And right now, the best thing we have is the simulations. The simulations which show reasonable results. And to how long it lasts is inspection. So you inspect, and with inspections, you see the evolution of the problem, and then you predict, okay, so with this level of damages, I'm losing this amount of production. And then you see when the curve of the cost of repair intersects with the cost, and you decide that's the sweet spot. So here's the maintenance.
Here's the trouble, Rodolfo, with that approach. And so that approach is used in lightning protection all the time. Like they want to go do a 5-year experiment on to see if this works or not. The problem is the industry is growing so fast. In Brazil, the industry is growing faster than it is in the United States. It's going to explode. The amount of money going into Brazil to build wind turbines is insane at the moment, which is great for Brazil. But if you start making yourself several thousand turbines, say it's 1,000 turbines a year, 2,000 turbines a year, 5,000 turbines a year, and you miss, you have a huge problem. And then you're right. Then the inspections become the number one priority to go out there and inspect. You should be doing inspection automatically.
Yes.
But what's happening is they're doing inspection plus an inspection plus an inspection because they have so much degradation they can't keep up with it. And they're trying to put a curve. Engineers are in the front office back there, or in the back office, sitting there going, okay, this is year 3. I have this much erosion. Next year, I'm going to have twice as much.
But yeah, go as Rodolfo, go and look at it.
Exactly.
Go and look at it.
You have to go look at it. I think that's going to be the key. I do think if you're not going to go buy some better LEP system, the robots are pretty good. Now, Rodolfo, I went to Lafayette. I watched this thing go on. The robot installation is pretty controlled, way better than I think is what's happening in the factory. Am I wrong about that?
No, I was the same boat with you. I have visited Ironis too. I have seen the robot. We have seen robotics robots. I think it's unavoidable that you have robots doing that. And it's unquestionable that a process done by robots, as any process done by a machine, it has less variation and it's going to give you a great result. I totally agree. I just would join that with the best material. And we have customers in Brazil right now that they're doing exactly this discussion. I'm going to do a big leading edge protection campaign. What material do I put? And they're trying. They're okay, I'll put 3 solutions so I can run for 2 years, compare, so I decide what to do on the rest of my fleet, because
but they don't want to do
have that.
They don't want to do it twice, though.
No.
Right. So that system sets up to do it twice.
No.
And that's where this conference, I think, comes into the symposium, and the people here should be able to direct an answer to, because a lot of turbines in Brazil in a particular area, sort of northeast Brazil, and so the weather's a certain way. We should be able to plug that into a model. Northeast Brazil, 4 megawatt, this OEM, and go, this is the right solution based on all the knowledge that we have. Am I crazy? I think that's the only way to do it.
That's the desire. That's what they want to do. But we are missing this theoretical answer.
Yes.
So they're doing practical.
Yeah.
They're doing all.
They're doing all practical,
all practical.
And the operators are doing it, which is the worst way to do it because they're already cut short because they don't have a lot of time to sit there and monitor it.
So
it's hard.
One of the late presentations yesterday by David Maniaci at Sandia, really talking about a lot of the IEA work and the Sandia work and the Learcat work that's been going on. I think he made a really good point about we have to do more modelling and we have to trust the modelling.
Yes.
Because when you start going to the field to hunt down a few tenths of a percent, it is nigh on impossible to do that with SCADA data.
It is.
So SCADA is a really valuable tool and can be used lots of ways, but you have to understand its limitations.
Right.
And trying to track, say, leading edge erosion losses of a small magnitude is incredibly challenging. And I think there's maybe been a little too much stock placed in it, rather than saying, well, we know how to model a wind turbine. We've clearly known that for a very long time because we have wind turbines.
Yeah, we do.
So let's just extend that trust and that confidence to use those models in slightly different ways.
Yes.
If we can design a blade and its aerodynamic characteristics with a model, you can also understand how it degrades with a model as well.
But you Nicholas, you're taking it from the blade designer, which has used a BEM model, into a computational model. And I think for a lot of operators who haven't worked with power curve before, they don't realize the power that sits in that model.
Yeah.
That if you have an actual blade scan, which you do, so you're not guessing at what the shape is. You're actually taking the real model and applying real damage to get a real number out of it, something they couldn't measure with the SCADA system.
No, exactly. And I think there's been a lot of focus on the Learcat project. So the team at DTU, like the Learcat team at DTU, Alexander, for example, he made a presentation yesterday looking at the CFD results, these really amazing CFD results of modeling the full 3D erosion in CFD and looking at how the lift and the drag changes, the flow patterns, or the buildup of the turbulence. And these tools are super powerful.
They are.
But you've then got to look, how do you plug that into some of the industry standards?
Right.
Because the industry standard is still BEM, blade element momentum. That's how you certify turbines. But you
can't use that to do these fine measurements
No.
and look at leading edge erosion. That model will not produce accurate results.
You've got to supplement it with the higher order models.
Yeah.
But, like lots of things, each tool has its place. So, to me, the job of the engineer is to bring all the tools at your disposal together, understand the limitations and the benefits,
Right.
and then fuse them to get the best answer.
Where can people go to see about Learcat? Where would you go on the web?
So there's a LinkedIn page for Learcat. There's also a project site on the DTU website. So if you just search for Learcat on LinkedIn, that's probably a good
Okay.
good
It's
way to
important
find
for
it.
operators and engineers involved in blades to get to that site to see what's going on, to understand what the state of the industry is, because there are some powerful tools. We can argue about what LEP solution we want to put on. However, we shouldn't be arguing about what the losses are and what turbines to go fix. I think that should be done, and in my opinion, should be thrown on VGs while you're at it, because I think it makes the lifetime longer.
It's a really good point, and actually, to throw a little bit of a curve, but we're talking a lot about leading edge erosion. That's the seminar here. But what about contamination?
Exactly.
So contamination, that's kind of anti-erosion. You're building up the surface. But aerodynamically, it's kind of the same thing in lots of ways. It's losing your lift, it's increasing drag.
The same problem, right? And we used to get pictures from Brazil. Can be pretty dirty at times. Oklahoma, Texas can be, the blades can be pretty dirty depending on the time of year until it rains. Basically, India can have the same issue.
The nice thing is that a lot of the techniques and things that we're talking about for erosion, they can be transferred to think about contamination. The only real issue is that I see is you can't put leading edge protection on to solve contamination.
No.
Because it's building up on the surface. Okay, maybe we could talk about really hydrophobic coatings and all these kind of things, but in general, you can say leading edge protection doesn't stop contamination.
Don't get me started on hydrophobic coatings, because I think we're having all kinds of discussion about that, but you're right?
Yeah.
This is it's wintertime. It's February right now, right?
Yeah.
We're in Denmark. It's snowing today, of course. Every place I go, it snows. When I went to Lafayette, it snowed. But those coatings, when you started adding any coating to a blade, isophobic coating, hydrophobic coatings. Leading edge erosion is a different animal, and I think you change the properties based on what I saw here today. You're going to change the properties of leading edge erosion.
Yes, yeah, exactly. They are linked, and contamination is a difficult one to deal with. It's also super localized. We see some blades, particularly up in like Norway, Sweden, 5-6 years old. They look perfect. They look in
Isn't
really
that
nice
insane?
condition.
It's true.
Yeah, but other blades, they've got proper crusts on the leading edge. But that's, you're mentioning VGs. That is where VGs can really come in.
Yes.
And you see quite a few turbines out there with VGs towards the tip. And their main purpose is to give robustness to the power curve.
Right.
Because when you have contamination or erosion, it damages the aerodynamic performance. It's harming that boundary layer over the surface.
Yes.
And the VG is there to re-energize the flow and recover the lift that's being lost. So a VG doesn't care if it's erosion or contamination, it will still recover losses. So again, you do need to think as an operator about LEP, repairs, inspection, but also upgrades, aerodynamic upgrades, because there's a lot of things you can do. Yeah.
But that comes out interesting question. Again, why the OEMs doesn't put that on the factory already?
I think that's a really...
That's a great question.
One thing, we're talking about the maintenance of the leading edge.
Yeah.
If or the OEM, when it sells a turbine, it says, you have to consider every 4 years repaint the leading edge. The operators will just do what the manual says.
Yes.
I don't think they'll say, I want to do that. No, they'll do what the manual says. So if they sell the turbine with a maintenance plan,
Yep.
the owner they will put on his business case. If he decides to buy the turbine, he just follow the business plan, and that's it.
Your point about VGs in the factory is an interesting one. I would say, again,
It
anecdote.
isn't cheap because on the first 130,
Yes,
more and more are doing that right now, but towards the cheap, I have seen no one do.
You don't see that so much. I would say
Gamesa
Siemens put on quite a lot.
has done it more recently.
Yeah.
That's the only one I really have
Tends
seen
to be
it.
as an aftermarket from what I've seen.
Yeah.
And that's just because I think, firstly, the knowledge level has been increasing quite dramatically in recent years because of things like the symposium we're at now. So the knowledge of how a VG can help you has certainly improved. I don't know that it's a cynical thing to say, but I think OEMs really like their service business. They make a lot of money from
service. I just saw
service.
Vestas' numbers, and they have a separate line item for service.
I think
It's
given
amazing.
the choice, they'd maybe prefer to put some parts on as a package they sell separately a few years down the line.
Sure, it's all money.
But aerodynamically, yeah, as you say, Rodolfo, most new big blades have VGs in the root anyway. Towards the tip, it's a bit different between the OEMs, for sure. But they can really help.
As you said, they can help to give robustness.
Yes,
to
it's
the
the
power curve. It's not going to increase, but it's going to protect it from the degradation.
it's recovering
that you have.
loss.
Yeah.
Yes, recovering.
Yeah.
Minimizing the effects of possible loss.
Yes, exactly.
Now, the best new product that Rodolfo and I were talking while you were out for a minute, Nicholas, was the best new product we've seen here so far is this company called Helicoid. I'm going to pronounce, I can't pronounce it because I'm American, but it's spelled Heliccoid. Helicoid?
Helicoid, yeah, we'll go for that.
All right. So the presentation started off, we're from Helicoid. We're based in the United States and the UK, and we're making pickleball boards, paddles. Well, I don't know where this discussion is going to go, but it's going to be interesting. Let's go. So the technology, I'll describe it as a technology. The technology is they're using the fiber construction of a shrimp, like the little critter that you eat, right?
Yeah.
So on some of them, they have this hammer device that they use to repel crabs because crabs like shrimp, evidently.
Yeah.
So these shrimp have these hammer devices which have this fiber that's really hard. Now, I guess they can use it to crack the shells of these crabs and defend themselves. But when they start looking at this fiber construction, it's really tight. Okay. So there's not a lot of other stuff. It's almost all fiber. And what they realized was if they took unidirectional fiber, and instead of going 0, 90, 0, 90, 45, you go 0, 30, 60, 90, something like that, where you have less space, less resin rich areas. that it makes it extremely tough.
Okay.
And when you rain erosion that material without any coating on it at all, you don't get the punch through.
Okay.
So it's the uni plies and the 090 plies that we put around the leading edges today, if we have them, or just glue joint, that we punch through. So when Rodolfo and I saw that, it was like, here we go.
Yeah.
So even if the LEP fails, you're probably not going to, it's going to give you a longer time before it eats through the laminate. We have to do a structural repair. So it lends itself to robotics that, okay, I see the coating is missing. I'm going to call Arones. They're going to be here, in 3 months. At 3 months, it's not going to eat through that laminate because it's designed in a different way to last longer to rain erosion. Rodolfo, is that the logic there?
That's the logic, and I think that's genius, because we go back to the same discussion to have time to plan the maintenance on the right time.
Yes.
So, and that's a big difference. We're discussing that also. Doing the repair for only the paint costs X. Doing the repair for the paint plus the laminates is going to cost between 2 to 3X.
Yes.
So you're just talking about doubling, maybe 3 times the cost, the cost and time of the machine stop it. And you have a material or you have a construction that can protect you from that. So you have time to do the repair before you reach this 2-3 times penalty. That's great.
The pictures that they were showing was of a standard leading edge design or fiber design, right? And then they applied this material over it as a
couple the
like 2 layers of this stuff.
It was they did a reference sample, like 6 layers normal material.
Oh, yes.
And the other one 4 layers normal plus 2 layers of their material.
Exactly.
And
so it would
very
replace
nice
some of the structural plies, or could be secondarily added, because how much of this material would you really need on a blade?
Some plies.
Half a meter of it wide, maybe? It wouldn't be necessarily, you're not using millions of dollars of this material.
I would consider that as a leading edge when you do a leading edge protection. Just
part of the protection plan.
Same width of the paint. So we're talking 200 millimeters, 300 millimeters maximum.
Yeah, you don't need to cover more than that.
Yeah,
it's
a little amount. It's a little amount.
So it's a small amount. It's something that would already fit into the manufacturing process. Whether you could inject resin into it, whether it flow right, and all those things have to be worked right. And that's when you have tight fibers like that, it can be a little bit difficult to get the resin in between them. But the logic makes sense that it could be a simple addition for an OEM, or even in a repair situation. Like if I had a cracked open leading edge, I could repair this material. So I'm trying to get to my 10-year lifespan in America, I would do it with this material. In fact, I probably wouldn't go fix the LEP 8 year 9. I would just let it go because I know I got probably a year with this stuff.
Can protect. Apart from you might be losing lots of AEP.
You're going to lose a lot of AEP. But at that point, the way the Americans run their turbines, Nicholas, you don't you don't want to know. But I do think there is a plan to get more power out, right?
Yes.
And I think overall, it's an overall number.
Sure.
This
is a perfect application for composites, right? Which you can put the fibers wherever you want them, whatever orientation you can do it.
So the pickleball solution actually turned into something real. So that presentation, which didn't start out on the best foot, in my opinion, all of a sudden at the end, I'm like, holy moly! I think that's
good.
Is it me, Rodolfo, over here? No, the 2 guys like looking at one another like, wow, this is cool. Because I do think that kind of technology can help buy us a little more time to get to whatever this magic LEP solution is going to be, which we don't have today.
Well, there was another presentation yesterday on metallic leading edge research.
Yeah.
So, obviously not a new concept.
No, metallics are hard.
And they were showing, obviously the upfront cost is going to be a lot higher, but lifetime cost should be much lower. So yeah, it is. It's you don't seem so sure.
I think the concept is right, but the implementation proposals, I think it lacks something still. I think it's complicated.
It's complicated. In a manufacturing,
much more complicated than the proposal.
Yeah.
But yes, I think that's the point. Maybe as we discussed, maybe we should have some focus. So on better materials. On different approaches to really extend the life, or to have a cost-effective material that gives us this maintenance plan that can be really predictable and affordable.
Yeah, I mean, I'm not sure you need to go full metallic leading edge on most onshore sites. It probably is overkill.
When the discussion about metal leading edges come up, I thought we are still in a new frontier. We have not got to a solution. We haven't arrived at a solution. We're still in the middle of a solution. We're using a solution that was on propellers back in the 1930s. Yeah. That's kind of where we're at right now. Like, well, right, we're trying everything.
Yes.
That we should keep ourselves open to everything. Yeah. And if it's a composite solution, if it's a leading edge protection coating or a shell, or maybe it's metal, who knows?
Yeah.
But we got to hurry. And
it's a difficult one, right? Because you don't want to stimulate innovation. You don't want to stimulate research.
Sure.
However, we can't pretend that the wind turbine industry is a cottage industry anymore.
No.
The number of turbines that are being installed means that we do have to speed up.
We have to speed up.
I don't think we can have 10, 15, 20 competing LEP solutions that have vastly different properties and maintenance regimes, because there's just too much choice. And then every time an operator wants to decide on a solution, they don't really know what to pick. They then have to set up their own test campaign because there's not enough data out there. And then I just feel like we just keep going in circles a lot. So yeah, there's that balance, which you have to innovate, you have to try new things, you have to open the box, but we also have to have a solution that surely a lot of people agree works.
So that gets to my point about time frame. And one of the sort of pain points for me watching this is I know how painful it is for operators to deal with this and all the tools and resources they're trying to go get. At the same time, the academic part of this is out to 2025, 2026, which is fine. I think that's fine, but we're in 2024. We need solutions now. We gotta somehow
how many gigawatts is going in next year?
Yeah, way more than we even want to think about, honestly, because the consequences of having leading edge erosion problems offshore gets super expensive. In the United States, the opposition to offshore wind is at fever pitch at the moment. If they had to drag back blades to get repaired next to the New York, Boston, Philadelphia corridor, that would erupt. And you can't have that. I think as an industry, you can't have it. Maybe as an OEM, you could survive it. But as an operator, I don't know if that would really help your case.
But, I think the kind of event we're at now at this symposium, it is bringing lots of the right people together. Operators, OEMs, academia, third parties, all have to be talking together.
Right.
You need to share as much knowledge as possible so that people don't have to go and repeat a test all the time because they want their own data.
It's true. I mean, it's nice to have your own data, but that data ought to back up what is published.
Yes.
Right? It's sort of that validation piece. Yeah. Fine, go run the test. And we're going to go visit the R&D test systems rain erosion facility that are building at DTU, which is supposedly magnificent. It sounds magnificent. And we're going to go tour that tomorrow. So I'm really interested to see how tight the controls are. This is getting back to the variability problem. Rain erosion testing, one of the complaints obviously is every rain erosion test facility that's not sort of R&D test systems rig gives you a different result. R&D test systems has narrowed that down quite a bit for sure. Again, the variability is too much. And that's why an OEM goes out and repeats these tests, is because they know I can get a different result.
But it's a big time suck that we can't necessarily afford.
No, but if I'm an OEM today and I don't have an internal rain erosion test set, I know where I'm going.
Yes,
I'm coming to Roskilde. I'm going to the DTU rain erosion facility because they know what they're doing and they're going to have the best facility in the world, and the consistency of that test should be better than anything else you can get. And even just talking to some of the people that work there, their knowledge of rain erosion and the types of variables that apply in that test was astounding. I've been around rain erosion testing a long time, almost 30 years. So I've seen a lot of it. That is going to be crazy good.
Great.
Yeah. Great. Yeah. It's fantastic. So Rodolfo, Nicholas, This has been fantastic. It's great to see you
Yeah,
in
likewise.
Denmark. I'd like to see you someplace where it's warmer. We got to get to
Come to
Spain or Brazil. We got to get to Brazil.
Always gets snow, you're going to the wrong place. Go to Brazil, there's no snow anywhere.
Yes. Yeah, we should go to Brazil sometime. But yeah, I appreciate you having you on the podcast, and this has been fantastic. So maybe we'll see you here next year
Absolutely.
for the 6th
Thanks a lot,
symposium. All right.
For sure.